So far in organic, we spent our time trying to draw Lewis structures for organic molecules and then learn some of the shortcuts that we can use to represent those molecules. What we haven't really done is to talk about why we believe those structures are the way that we draw them. What we're going to do here and in another lab period is to begin to get an understanding of why it is that we believe those structures are in fact correct. We're going to begin our story with a technique called mass spectrometry. In 1922, Francis William Aston was awarded the Nobel Prize in Chemistry for his work on isotopes. Here we see some of his work on neon. What I'll say is that he used an instrument called a mass spectrometer, which we'll take a look at in a moment, to measure the isotopes present in a sample of neon. You'll notice that when he ran this little instrument, he got 3 peaks. One peak had a mass of 20 AMU. You'll recall from general chemistry that AMU stands for atomic mass units. That's used when we're talking about individual atoms. If we were talking about a mole of atoms, we would instead say grams per mole. He got a large peak at 20, another one at 21, and yet another at 22. Well, we'll tabulate that data, and what you can see is that although neon has 3 different isotopes, the one that has a mass of 20 represents 91% of all the neons on planet Earth. For that reason, the area beneath that first peak happens to be much larger than the area beneath the other 2 peaks. The device that he used is called a mass spectrometer, and I've got a little pictorial representation here. What we're going to do is we're going to take a sample of, say, neon or possibly some organic molecules, and we'll pass them into the instrument in the gas phase. We'll keep the system under vacuum, and the reason for keeping it under vacuum is we want to keep those molecules as far apart in space as possible because our mission here is to measure their masses, not to have them react with each other. Well, as they go into the instrument, what we're going to do is to pass a beam of electrons toward those molecules. Those electrons are generated on a filament and shot toward the molecule. As the electron beam encounters the molecule, it's entirely possible that electrons surrounding the molecule itself will be ejected. When that happens, we're going to produce cations. What we'll do with the cations is we're going to take some accelerating plates and put an electrical charge on them to try to attract the cations in this general direction. As the cations begin to move through the instrument, what we will then do is to pass them through a magnetic field. As they encounter that magnetic field, all of a sudden, those charged particles are given a shove. Now, if the particles don't weigh very much, let's say not very massive, kind of like I was in elementary school, then they can get pushed around quite a bit. And so what happens is that beam will be deflected very far. Well, I've gained a lot of weight since elementary school, and so that makes it a little more difficult to push me around. And so what you'll see is that those molecules that are heavier are not deflected nearly as far. So we can actually separate these 2 different massed particles and get those guys to show as a printout on a mass spectrum. A spectrum is simply a list, if you will, of all the different masses of the ions. The height of the peak tells you how many of those particles are actually hitting the detector. This is a typical mass spectrum, and it's of a relatively simple compound called methane. I know you've been spending a lot of quality time memorizing names of organic molecules, so it comes as no surprise to you that methane is CH4. If you grab your periodic table of science and look up the nominal mass of carbon and hydrogen, what I mean by nominal mass is we're going to round those numbers off to whole numbers. If you add 1 carbon and 4 hydrogens together, what you come up with is a molar mass of 16 AMU. So that's for a single methane molecule. If it was an entire mole of methane, we would say 16 grams per mole instead. When you look at the spectrum, notice that there is a ginormous peak at 16 on the mass scale. Well, that's given the symbol M+. And all M+ means is that's the molecular ion. The molecular ion is simply the entire molecule that has lost an electron. As you might guess, as you knock an electron out of a molecule, it becomes unstable, much like myself. Whereas I've begun to lose hair follicles, I think this molecule is going to begin to lose hydrogen atoms. If you remove one hydrogen from methane, what you're left with is what's called a methyl group, and that methyl group has 1 carbon, 3 hydrogens, and a mass of 15. Oddly, if you lose a second hydrogen, you're going to have a methylene group, CH2. Lose another one, and it's a CH, and then finally the carbon itself. Now, the careful observer will note that there's also a peak at 17 AMU. What's up with that? I thought methane weighed 16. Well, you're right, but that's if it has carbon-12. It turns out that 1.11% of all the carbons on planet Earth happen to be carbon-13. So some of those methane molecules are going to possess a carbon-13 rather than a carbon-12. And if you notice, the ratio between the peak at 17, which is called the M+1 peak, in honor of the fact that it weighs 1 more than the molecular ion itself, the M+1 peak is 1.1% the height of the M+ peak. And the reason is because there's only 1 carbon present. Had there been 2, then it would have been 2.2% the height of the M+ peak. The next molecule I'd like to take a look at is bromomethane. Bromomethane is essentially methane that's had a hydrogen replaced by a bromine atom. It turns out that when you look at the molecular ion, you see not 1 but 2 giant peaks. Those 2 peaks happen to be separated by 2 mass units, and because they're separated by 2 mass units, the 2 isotopes of bromine, 79 and 81, well, a good mathematician would tell you 81 minus 79 equals 2. There are 2 mass units difference between those 2 isotopes. It turns out that on planet Earth, about half of the bromines are bromine 79 and about half are bromine 81, and so the height of these 2 peaks happen to be just about the same. In fact, this is often a dead giveaway that your unknown substance has bromine in it. If you have 2 peaks of equal intensity separated by 2 mass units, roughly where that molecular ion should be, then that tells you that you've got a bromine atom. Chlorine is another atom that has significant isotopes. What I see here is a spectrum of chloromethane. This time it's a chlorine rather than a bromine. But once again, you'll notice where the molecular ion is that there are 2 pretty big peaks, and once again they happen to be separated by 2 mass units. The reason they're separated by 2 mass units is the less massive peak happens to be chlorine 35, and the more massive peak happens to represent chlorine 37. Well, it turns out that 75% of the chlorines on planet Earth are chlorine 35 and 25% are chlorine 37. What that means is that the peak representing chlorine 35, the one that's less massive, happens to be 3 times the height of the one that represents chlorine 37. So if you get an unknown and it happens to have 2 peaks separated by 2 mass units, less massive peak happens to be 3 times the height of the more massive peak, well, that indicates that chlorine is present. Next, let's take a look at acetone. This little CO here in the middle, you know and I know, represents a carbon with a double bond to oxygen. Carbon's always got 4 bonds in its stable structures, and so that little portion of the molecule is called a carbonyl group. What I will say about acetone is its molar mass is 58. If you'll notice, there's a peak at 58, and so we're going to label that one as the M plus peak. It's the one furthest to the right on the spectrum, obviously with the exception of the M plus 1 peak, which is that tiny little peak that you can see at 59 AMU. So the M plus peak represents the entire molecule which has lost a single electron. So that's acetone itself. Now there are other peaks in the spectrum, and they represent the loss of various groups within the molecule. Interestingly enough, most organic compounds undergo fragmentation close to functional groups. So I've drawn a little zigzaggedy line right in between the carbonyl and the neighboring CH3 or methyl group. When that bond breaks, you're left with what's called the base peak. The base peak in this one happens to be at a mass of 43. The reason it's at a mass of 43 is if you take away that methyl group, everything that remains is 2 carbons, 3 hydrogens, and an oxygen. Grab your periodic table and prove to yourself that indeed that has a mass of 43 AMU. If you're wondering, dear Lord, what happened to that poor methyl group? Well, there it is at a mass of 15. Now, I'll say this. There are lots of other peaks in this spectrum, but the big deal is that one very common fragmentation is adjacent to functional groups. And it's very, very common that you will see a methyl group lost. And so it may be important to realize that a methyl group has a mass of 15 AMU. 58 minus 15 is 43. In your chem activity that we'll do in lab, we'll be playing with the molecule 2-butanone. 2-butanone, just like acetone, happens to be a ketone. So you can expect that it's going to break little bonds between the carbonyl group and the neighboring position. But we'll save that for lab, shall we? The molar mass of 2-butanone happens to be 72 AMU. Well, there's your M plus peak right at 72 AMU. Again, the M plus peak can be identified as being the one farthest to the right, with the exception of the small isotopic peak. There is a large peak. The biggest peak in the spectrum is always called the base peak. That base peak happens to represent a common fragmentation. I'm going to work with a couple of problems that have found their way into old ACS exams. There is a book that I've made reference to a couple of times called Preparing for Your ACS Examination in Organic Chemistry, the official guide. There are 2 copies of that available in the chemistry faculty suite area. Please know that there are like 54 people in the class, so you may want to get your own personal copy, but that's where you can get one for now. They're in 3-ring binders on a bookshelf in the chemistry faculty suite area. I've gone to the spectroscopy chapter, and problem 19 deals with mass spectrometry. The question asks, which compound would show major fragment ions at M over Z 73 and 59? Okay, first, don't be alarmed by that M over Z notation. Think of that as just being molar mass. And the reason I say that is this. The notation M over Z is for mass over charge. The reason they do that is if 2 electrons happen to come out of a molecule rather than 1, it's going to deflect that beam twice as far, and so what you will see is it's more relevant, the mass to charge ratio, as opposed to simply the mass. Having said that, it's almost always true that a single electron comes out of the molecule rather than 2, and so we're just going to think of that as molar mass and be done with it. What I want you to notice later is that each of these compounds possesses 5 carbons, 12 hydrogens, and an oxygen. The molar mass of each then is 88. Again, use a periodic table and prove to yourself that that's true. Well, what I'm going to do first is I'm going to notice that one major fragment ion happens to be at m over z 73. Let's take 88 and subtract 73 from it, and what I think you'll discover is what's left is a mass of 15. 15 happens to be the mass of one carbon and 3 hydrogens, or a methyl group. So in D, I have circled a methyl group, and the reason I circled this methyl group instead of that methyl group is because this methyl group happens to be directly attached to the carbon with the functional group. Remember that that's a common cleavage that organic molecules are going to do. Well, unfortunately in C, I also see a methyl group directly attached to the functional group. I also see it in B, but I don't see it in A, so I'm going to go ahead and cross out A as a reasonable possibility. All right, the next thing I'm going to do is I'm going to work with that major fragment at 59. If you take 88 and subtract 59 from it, the mass that you get is 29. 29 just happens to be the mass of 2 carbons plus 5 hydrogens, or an ethyl group as it's called. You'll notice that D has got an ethyl group in addition to the methyl group. Now, it's true that A has an ethyl group directly attached to the carbon as part of that functional group, but it doesn't have a methyl group directly attached. D has got both. D is your best answer. B and C both have methyl groups attached to the carbon with the functional group, but they don't have a simple ethyl group attached. Problem 21 is sort of similar. What I notice about this one is that, again, we're looking for major fragment ions, and our major fragments are 85 and 57. The careful observer will notice that there are 7 carbons in the molecule, 14 hydrogens, and an oxygen. And that's true regardless of which one you're looking at. They're all isomers. If you take 85 away from 114, what you'll discover is that that mass is 29. That may seem familiar. We had a mass of 29 in the previous problem, and what that was is an ethyl group. I notice that A has an ethyl group directly attached to the carbonyl of that ketone. B doesn't, C doesn't, and, well, by golly, D doesn't either. I think we already know which one it is. But just to be safe, let's take 114 and subtract 57 from it. When you do, you come up with 57, and 57 just happens to be the mass of 4 carbons and a total of 9 hydrogens. Yep, A is the right answer. So I hope you've come to realize that why mass spectrometry is important is, 1, you can help determine what molar mass is. The way you determine molar mass from a mass spectrum is to identify the M+ peak. That's the peak farthest to the right in the mass spectrum, with the exception of the small isotopic peaks. In certain cases, that M+ peak can be difficult to identify, but let's save that for Dr. Wadener's spectroscopy class. Fragmentation patterns are important as well. You'll notice that fragmentations are common in some spots, less common in other spots. So it's true that for organic molecules, commonly fragmentation occurs adjacent to functional groups. In simple alkanes, you can expect fragmentations to occur at branch points down the main chain. It might help to realize that a CH3 group has a mass of 15 and an ethyl group happens to have a mass of 29. Molecules containing bromine are going to have 2 peaks of equal intensity 2 mass units apart. So I'm going to go way on the right of the mass spectrum. If I see 2 really tall peaks separated by 2 mass units, I'm thinking, it's got bromine. If instead you've got 2 peaks separated by 2 mass units, and the one that weighs less is 3 times the height of the one that weighs more, well, that's an indication that you've got chlorine, because chlorine 35 is 3 times more abundant than chlorine 37. Finally, if you've got nitrogen in a compound, this is weird, but it's generally true that if you have an odd number of nitrogen atoms, the molar mass of your compound will be an odd number. In other words, when you identify the molecular ion, it's going to have an odd AMU listed. Most of the other organic compounds are going to have even numbers listed instead. Lastly but not leastly, it is possible to estimate how many carbons are present in a molecule. You can do this by doing the math and taking the ratio between the M plus and the M plus 1 areas. When you do, that is equal to the number of carbons present in the molecule times 0.0111. That's simply a reflection of the fact that carbon-13 is 1.11% of all the carbons on planet Earth. Later we'll take a look at some other techniques, try to get a feel for how can I tell what functional groups are present in molecules, how can I tell how the carbon chains are connected. But for now, molar mass is an important concept, and mass spectrometry is the best technique.